Epsilon Delta. All right. This is probably the absolute last calculus lesson that we're going to be filming this year. Yeah, I think so. Because what we're going to do tomorrow in the gym, we're not going to film. Thursday, not Thursday, Friday, I see you guys for like a short block of time. We're going to like do a little reflection and close out and do all the things. And then Monday there's no school. Tuesday there's something happening. It's like the diversity fair. Wednesday there's something happening. Thursday is field day, so I wouldn't see you then. And then Friday, you are officially, well, at the end of the day, Thursday, you guys are done as seniors. Yes. And then Saturday is graduation. And then I hop on a plane and fly to New York City, and we'll see each other again in August. Okay. All right, so for our final calculus lesson, we're going to go big. We're going to go big on this one, and what I can tell you is we're going all the way back to August. Very likely when you start your calculus experience in the fall, whether that's Calc 1 or Calc 2. Well, if it's Calc 1, you're going to do this thing called Epsilon Delta. It is the behind the scenes, like when we talk about limits, and you talk about proving a limit, and what does it mean for a limit to exist, this Epsilon Delta method is like the very ground. It is the foundation that all of calculus is built upon. I didn't do much with Epsilon Delta when I was a high school student in Calc 1. I didn't do anything with Epsilon Delta in like Calc 3 as a freshman in college. It wasn't until I took, it's called a real analysis class, and if somebody can turn that off, a real analysis class in graduate school that like Epsilon Delta and all of these analytical proofs came up. And Mr. Link, I don't know what your experience was with real analysis.
It was rough.
I hated the course. It is the only math course I have ever taken in my life. I hated this course. It was in graduate school. I mean, I was already like on the path of like, life is good, I'm gonna be okay. We talked about Lebesgue measure and Fatou's lemma. I don't know what Fatou's lemma is, don't ask me. And all these different things. And the title of the course was Real Analysis, and I was so angry about the course that I changed the title of the course in like on my notebook to that. I was just so angry about being in the course. There are ladies in the room. I've got to get away from this. But I remember like Professor Fox coming in and he's like, oh, we're going to start off talking about limits. I'm like, limits? Oh my God, why are we talking about limits? I'm so good. I know how to evaluate limits. I could do limits on a calculator, which was big in the 90s because we didn't have a lot of calculators. I could do limits by, I knew a lot about graphs, I knew about parent functions, we did that before. Mental math, yeah, mental math I was good. Algebraic manipulation, like factor cancel. I knew L'Hopital. L'Hopital and I were like best friends. Squeeze theorem, I could squeeze some things. And then we get to this Epsilon Delta method and just life fell apart. Life absolutely fell apart. And I want to make sure that over the course of the next 28 minutes, that you have that equally miserable experience as well. No, I want to make sure that whether you take Calc 1 in the fall or someday you're in that real analysis class, sorry, that you have at least seen the words. You're not going to be the kid that comes in and who's like, what's epsilon? What's delta? No, we're not going to do that. So here's the thing that you need to understand. David, you okay? All right. We're going to talk about the fact that, like, if I say the limit as x approaches c of f of x is equal to L, right? What am I saying? What does that really mean? The limit as x approaches c of f of x is equal to L. How would you, I'd love to hear from somebody, how would you explain this to somebody that hasn't taken a calculus course? Graphically, what's happening? Lewis, what's happening?
When the function approaches from x to the point equal to point, which would be L.
Okay, so what I heard you say is you get a function, And the x values, right, you're on the x-axis, the x values are approaching some number c, right? What's happening to the y values is they're getting closer to this number L. Are we okay? And the function has to be continuous for this limit to exist?
Yes.
No.
Oh, no, sorry, no.
A jump discontinuity would be a problem. There is a discontinuity that's allowed, and this limit would still exist. A hole. Right, your graph might look something like this. Here's x equals c, here's the point c comma L. As the x values get closer and closer to c from the left, the y values get closer to L. As I get closer and closer to c from the right, y values are getting closer to L. We're okay? All right, now a different problem shows up if you've got, I heard somebody said, like a jump discontinuity. And the problem is, here's x equals c, and if this is the point c comma L, as I get closer and closer to c from the left, the y value gets close to L, we're okay? But if I get closer and closer to c from the right, the y value isn't getting closer to L, it's getting closer to something else. Limit does not exist here. Limit as x approaches c of f of x does not exist, and I hope all 10 of the friends and everybody watching at home were okay. And we could do, well, a hole is an example of a removable discontinuity. Big picture, we're okay? This is the epsilon delta definition of limits. This is where we're going to go next. All right, so with all that said, here we go. Epsilon delta says this. F of x approaches L as x approaches c because for any epsilon, that little symbol there is epsilon. What's it called?
Epsilon.
Epsilon. We can make the gap less than epsilon by taking delta sufficiently small. Yeah, I just said that. By contrast, the function figure number 2 is a jump discontinuity at x equals c. All right, so here's what we're talking about with epsilon. We've got some number over here. We're saying that this is the limit as x approaches 2 of x squared, and you guys know that the limit as x approaches 2 of x squared is 4, right? I would hope at this point no one doubts that. We know it's 4. How did we get 4? This is direct substitution. You plug into. But the thing with limits, I'm not asking the question what happens when you plug into. I'm asking the question what happens as you get close to 2. So if I had my calculator, what would you do? If you had access to a calculator, how would we find this limit? You'd graph the parabola and then numbers close to 2 from both sides, like 1.9, 1.999, 1.99999. We'd make a table and we'd look at the values and we'd see that they're getting closer to 4. We'd pick values to the right of 2, 2.1, 2.01. We'd watch, they get close to 4. We'd say the limit as x approaches 2 is 4. We're good? The analytical definition says this. Here's x equals 2. And here's y equals 4. The epsilon, someone says, for any epsilon greater than 0, for any value of epsilon, for any epsilon greater than 0, what you do is you're going to find like a little interval around the 4. So this is like 4 plus epsilon to 4 minus epsilon. I'm going to tell you whatever the epsilon is, and what you need to do is find a delta around here. That this is like from 2 plus delta to 2 minus delta. I'll explain this a little bit. For any epsilon, you can find a delta such that if the x values are no more than delta away from 2, the y values are no more than epsilon away from 4. This is the epsilon delta definition of limits. Now let me say that again. You're going to be told for any epsilon greater than 0, you want to think small numbers like 0.1, 0.01, 0.001. No matter how small this epsilon is, if I imagine drawing my little interval around 4, I can find a delta. You give me the epsilon, I can find a delta. And when I find that delta, what I'm telling you is, for any value of x within this range of 2, if I plug those values into the function, the y values will always be within epsilon of the number 4. You can make epsilon really, 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 really small, and I can find the corresponding delta. And inside that delta range, all the outputs are within epsilon of 4. I just want to make sure you're hearing this a couple of times. We're going to do 1 or 2 little proofs, and we're going to call it a day. I'm looking out for the future versions of you. Would everyone agree that this is probably not super comfortable right now? Okay, but this is what it means for a limit to exist. You tell me how close you need to be to that number 4, and I can always find a corresponding delta that's going to match this. So here we go. Stephen, I'm going to be over here. So this is where you want to make sure you're getting some good notes. Limit as x approaches 2 of x squared is equal to 4. If that's true, then what we need is this. For any epsilon greater than 0, we can find a delta such that for all x less than delta, the absolute value of x squared minus 4 is less than epsilon. This is how you would start a proof. You can give me any epsilon. The epsilons are talking about the difference from the number 4. I can find a delta such that for all x's in this interval, the difference between x and 2 is less than delta. The x squared minus 4 is going to be less than epsilon. This is where we are. Okay. So, let's go with that. I had my solutions. They're over here. All right. So here's where we're going to start. You normally start in this direction. You start with the y values. If the absolute value of x squared minus 4 is less than epsilon, I'm going to rewrite this as the absolute value of x minus 2 times the absolute value of x plus 2. Right, just a little factoring. The absolute value of a product, I can break it into the product of the absolute values. The reason that I'm doing this is I want to get this x minus 2 to show up. What we're looking for is a delta such that whenever x minus 2 is less than delta, x squared minus 4 is less than epsilon. Having the x minus 2 show up is really important. So what we're going to say is this. If the absolute value of x minus 2 is less than 1, it doesn't have to be 1. There's nothing magic about the choice of 1. I could say absolute value of x minus 2 is less than 3, 4, whatever. Well, if the absolute value of x minus 2 is less than 1, then it means that negative 1 is less than x minus 2 is less than 1. Adding 2 to everything, we get that 1 is less than x is less than 3. If I choose my epsilon to be less than 1, then the x values have to live between 1 and 3. But if the absolute if x is between 1 and 3, I need to circle back around up here. What do we know about x plus 2? If 1 is less than x is less than 3, then x plus 2 is less than 5, but it's greater than 3. So this means that the absolute value of x plus 2 has to be less than, what's the biggest the absolute value of x plus 2 could be? 3 is less than x plus 2 is less than 5. The absolute biggest the absolute value of x plus 2 could be would be actually 5. Putting all that together, what this means is that the absolute value of x minus 2 times the absolute value of x plus 2, I can rewrite that and say this means that the biggest this can be is 1. The biggest that this guy over here can be is 5. Whoa, I just blew it somewhere. Ah, sorry. The absolute value of x minus 2 times 5 has to be less than epsilon. And so the absolute value of x minus 2 is less than epsilon over 5. Stay with me just for a second here. You gave me an epsilon. You could pick any epsilon that you want, as long as it's a positive number. My goal is to make sure that I find the right delta so that the absolute value of x minus 2 is less than delta. If I find the right delta, then the absolute value of x squared minus 4 is always going to be less than epsilon. And from that, I can then conclude that it means that the limit as x approaches 2 of x squared is actually going to be 4. So we started by looking at the comparison to epsilon, do a little factoring. And then I think the strange part in the beginning is like we're making an assumption about the absolute value of x minus 2. If the absolute value of x minus 2 is less than 1, then it means x minus 2 is between -1 and 1. That means that x is going to have to be between 1 and 3. Adding 2 to both sides, 3 is less than x plus 2 is less than 5. That gets me a statement I can make about this absolute value of x plus 2. So what I know now is that the absolute value of x minus 2 is less than epsilon over 5. The conclusion is going to be to say then let delta be the minimum, whatever's smaller, between 1 and epsilon over 5. As long as the delta that you pick is smaller than 1 or epsilon over 5, whichever one is the smaller one. Let delta be the smallest of these two. Everything fits, and you get that the absolute value of x squared minus 4 is less than epsilon. This is a proof. This is an epsilon delta proof. If that just went, part of that is my fault, and part of that is it's just epsilon delta. It's just the thing that you do. And maybe you hope and pray that it doesn't happen to you in Calc 1. All right, let's try another one. Yeah, this is actually, this, for reals, Calc 1. Calc 1 in a college level math course probably involves epsilon delta. Okay, so let's try model problem number 2. Before I say anything at all, go back to the definition of epsilon delta, see if you can like wrap your head around this and explain it to somebody near you. What's the epsilon? What's the delta? What's the point? Maybe the other questions are why God why? I hope everybody is 100% okay with this original limit statement. Is that a safe assumption for me to make? That everybody in the room knows the limit as x approaches 9 of 2 plus the square root of x is going to be 5. Right, like, we can all agree on this. We know this limit is 5. I could ask any of the future calculus students that happen to be in the room right now, what's the limit? And I bet you guys would all plug in 9. And you'd say the answer is 5. We know that it's 5. You either know what the graph looks like, and this is a graph I would expect you to know, or you know that you can plug in, or you build a table of values. All the options are on the table. Let's just get a quick little sketch here. 2 plus the square root of x. What does that graph look like?
X or the
Right, square root of x normally starts over here, but we're going up 2 spaces. So this is 2 plus the square root of x. Here's 9. We know that the y value there is equal to 5. But I want to map this over to the y-axis and say here's y plus 5. The epsilon delta method says this. For any epsilon greater than 0, the epsilon talks about the y values. For any epsilon greater than 0, we can find a delta greater than 0 such that the deltas have to do with the x values, such that if the absolute value of x minus 9 is less than delta, then the absolute value of square root of x plus 2 minus 5 is less than epsilon. This is the direction of the proof. Someone's going to give you an epsilon. So we're saying over here that the absolute value of y minus 5 is less than epsilon. Here are the deltas. The absolute value of x minus 9 is less than delta. They give you the epsilon. You can find the just right data for this to work. Just right delta for this to work. Okay. So just like we did over here, you start with the y values. So start with the absolute value of square root of x plus 2 minus 5 is less than epsilon. Your goal is to be able to make a statement about x minus 9, the absolute value of x minus 9, because this is going to tell you how to build the delta. Okay, the legal things we can do. How about rewrite this as square root of x minus 3? Legal. But it doesn't involve the absolute value of x minus 9, and this is where we want to get to. We've got to get here. So I need some legal things that you can do here that will bring this absolute value of x minus 9 to play. Squaring both sides won't actually make this x minus 9. Good try. There's something else you can do that would make this x minus 9 that is algebraically legal. And it has to do with the fact that there's a square root. It's been a while. There's a legal thing that you can do that, because we're dealing with square roots, you might want to consider. It has been a super long time. Multiplied by the conjugate.
Oh, you multiply.
Let that sink in for a second. Going through all the memory banks here. Back in August when calculus was easy. Conjugate, multiplied by the conjugate, that meant something. What's the conjugate of square root of x minus 3?
Square root of x plus
Square root of x plus 3.
Oh, yeah.
The legal way that you multiply by the conjugate to maintain your balance is you don't multiply this by the square root of x plus 3. That's bad. You multiply by the square root of x plus 3 over the square root of x plus 3. Are we okay? Okay. There once was a time where that was like natural, and we did it all the time. Leo's, I need to be convinced. Why can I do this?
One.
Because this is really one. Andrew, I need to be convinced. Why am I doing this?
So you get x minus 9.
Because we need to get an x minus 9, absolute value of x minus 9 showing up in this problem. So, all right, if we do that, that's just 1. Well, what do we get? Square root of x minus 3 times the square root of x plus 3. Hey, good news. That's x minus 9. In the bottom, we've got the square root of x plus 3. And I want this to be less than epsilon. And so this is the part where it gets a little bit weird. A little bit weird. We're going to make an assumption. So if you're like, it already got weird. We're going to assume that the absolute value of x minus 9 is less than some number. Any number. I don't care what number you pick. 1 is a great number. What you're saying when you say 1 is that let's assume that I'm able to go, absolute value of x minus 9 less than 1 means I can go as far as 1 space to the right and as far as 1 space to the left. If that 1 is too big, I'm going to make it smaller. I know, it just seems weird. You're like, it's too big, so you're going to make it smaller? Stay with me. So assume the absolute value of x minus 9 is less than 1. That means that negative 1 is less than x minus 9, which is less than 1. Add 9 to everything, just because we do. That means that 8 is less than x is less than 10. What I need to get, hold on, Lewis. I'm trying to find a way to rewrite this square root of x plus 3, which happens to be in the denominator. If we assume the absolute value of x minus 9 is less than 1, then negative 1 is less than x minus 9 is less than 1, and we get that 8 is less than x is less than 10. And everybody okay? We're going to do legal things here. That means that the square root of 8 is less than the square root of x, which is less than the square root of 10. Still doing legal things. I'm trying to build the square root of x plus 3. That means that if I add 3 to everything, I still get the inequality to be true. Right? Just adding 3 to all the sides. We have a problem though. The absolute value of x plus 3 is in the denominator. We know, based on this assumption, that 3 plus the square root of 8 is less than the square root of x plus 3 is less than 3 plus the square root of 10. I need to know about 1 divided by the square root of x plus 3. What's true there? Take the reciprocal of everything. 3 plus the square root of 8 is less than this guy, which is less than this guy. Take the reciprocal. What happens? Right, we can take 1 over 3 plus the square root of 8. We can look at 1 over 3 plus the square root of 10, but you need to be careful. You just flipped everything. Which means that the signs switch. So you need to tell me, what is it that you now know about the absolute value of 1 over the square root of x plus 3?
The max it can be is 1 over 3 plus the square root.
Right, it has to be less than 1 over 3 plus the square root of 8. And so here's what we know. If the absolute value of x minus 9 over the square root of x plus 3 is less than epsilon, then pulling all this together, I'm going to rewrite the square root of x minus 9 over the absolute value of x plus 3 as the absolute value of x minus 9 times the absolute value of 1 over the square root of x plus 3. We know that this guy here has to be less than, always less than, this guy here. So it must be true that that it's less than the absolute value of x minus 9 times 1 over 3 plus the square root of 8. I need for this to be less than epsilon. So in order to do that, I multiply both sides, and what I get is that the absolute value of x minus 9 is less than 3 plus the square root of 8 times epsilon. And I know it feels like you're done. We're not done. Here's why we're not done. What we're after is the delta. What's the right delta? What's the range around the x values that I set so that all my y values are always inside this epsilon? We started off life by making an assumption that the absolute value of x minus 9 is less than 1. We reach a conclusion at the end that says, oh, the absolute value of x minus 9 is less than all the stuff here. So what's the delta that you pick? You pick delta so that it is the smaller of the two, because I need to guarantee that all the outputs fall within that epsilon. So the conclusion is going to be, let delta be the minimum of the one that you used and 3 plus the square root of 8 times epsilon. You give me an epsilon, I know how to build the right delta. You say, Palamon says, oh, no. I need you to make epsilon smaller. I need you to be closer for me to be convinced that the limit exists. I'm going to make epsilon smaller. The good news is, I know how to build the delta. I either use the number 1, or I just say it's 3 plus the square root of 8 times the epsilon that Palamon gave me. And whichever one is smaller wins. That's the delta that you use. Of all the things that we've done this year, it is possible that this is going to make the least amount of sense. But I at least wanted to plant a little seed so that if you take Calc 1 in the fall or you take real analysis as a graduate student, when the professor says we're going to look at epsilon delta, you know that it's time to groan loudly. And that this might be the end of your career as a mathematician. No, it's not going to be the end of your career as a mathematician. But, ooh, darn. Okay, and for the sick and twisted folks that are in the room, tonight when you're like, gosh, what do I do because I don't have any homework? At the bottom of this page 2, there is a link to worked out solutions. Stephen, I'm really just talking to you. There's a link to all the worked out solutions for these 11 problems at the bottom. Okay? Stephen, Isaiah, other sick and twisted individuals, when you finish torturing puppies, maybe you want to go and like work on this instead.